In this video, we're going to use the properties of logarithms that we learned in the last lecture in order to solve equations. Here's a quick reminder of those three properties. The sum of two logarithms with the same base can be rewritten as a single logarithm if you multiply the inputs. The difference of two logarithms with the same base can be consolidated into a single logarithm if you divide the inputs. And for this last rule, let me read it from right to left. If you have a constant times a logarithm, you can bring that constant into the logarithm by making it the exponent on the input. Let's just jump right in. Our first example says log base 14 of 11x plus 3 equals log base 14 of 4 plus log base 14 of 2. If we can rewrite this sum as a single logarithm, then we can apply that one-to-one property. Left side I'm not doing anything with just yet. On the right side we're adding two logarithms with the same base, and our rule says that we can multiply the inputs. So this is log base 14 of 8, 4 times 2. The only way the left side could be equal to the right side is if the inputs are the same, because logarithms are one-to-one. So 11x plus 3 equals 8, 11x equals 5, x equals 5 over 11. Logarithms have domain restrictions, so we have to make sure that this is an allowable input. But if we put it into the left side of the equation, we get positive 8, and so we're okay. Let's look at another example that's going to use a different property. This says 3 times the common log of x equals the opposite of the common log of 8. I do have a single logarithm on each side, but both of them have coefficients other than 1 in front. We've got to get those out of the way, and that's where the last property comes in. We can bring those coefficients in front in as exponents. So I can rewrite the left side as the common log of x cubed, and I can rewrite the right side as the common log of 8 to the negative 1. And remember that a negative 1 exponent basically just finds the reciprocal of the base, so that's the common log of 1/8. Now I can use the one-to-one property. X cubed equals 1/8. Using extraction of roots, I get x equals 1/2 because the cube root of 1/8 is 1/2. 1/2 is an allowable input to the left side, and so we have our solution. May as well run through all of the properties once. This third example says the natural log of x minus the natural log of x plus 2 equals the natural log of 2/3. We'd like to consolidate the left side into a single logarithm, and when you subtract two logarithms with the same base, you can consolidate by dividing the inputs. So we can rewrite the left side as the natural log of x over x plus 2. Now the inputs must be equal, so x over x plus 2 equals 2/3. I would multiply both sides by 3x plus 2. Another way to think of this is to cross multiply. The x plus 2's cancel on the left side, leaving us with 3x. The 3's cancel on the right side, leaving us with 2 times x plus 2, which is 2x plus 4. Subtracting 2x from both sides, we get x equals 4. Make sure you can plug 4 into both of these. Natural log of 4 is okay. Natural log of 4 plus 2 would be the natural log of 6. That's also okay. X equals 4 is our solution. Let's do one more example where we use this one-to-oneness property. See if you can do this one. 2 times the common log of x equals the common log of 9. So first thing you want to do is bring that exponent in and rewrite this as the common log of x squared equals the common log of 9. And now we can set the two inputs equal to each other, so we get x squared equals 9. And we could subtract and get 0 on one side, or we could use extraction of roots. Using extraction of roots, we get two solutions, x equals 3 or x equals negative 3. However, negative 3 is not an allowable input to the left side, and therefore it's not really a solution. The only solution is x equals 3. So as a general theme, if all of your terms are logarithms with the same base, try to consolidate and use the one-to-one property of logarithms. But what if you've got a term floating around that isn't a logarithm, like in this example? This says log base 5 of x plus log base 5 of 3x minus 10 equals 2. The right side isn't a logarithm, so we can't use the one-to-one property as this is written. Well, in a case like this, what I prefer to do is rewrite the problem in exponential form after I get all of the logarithms consolidated. So on the left side, we can consolidate this into a single logarithm by multiplying the inputs. This is log base 5 of x times 3x minus 10 equals 2. And distributing, that's log base 5 of 3x squared minus 10x equals 2. Instead of trying to rewrite the right side as a logarithm, which is an option, I prefer to just use our translator. Recall that y equals log base a of x if and only if x equals a to the y power. So let's rewrite this in exponential form. The input to the logarithm goes by itself on one side, so the 3x squared minus 10x is going to appear by itself. On the other side, the base of the logarithm becomes the base of the exponential expression, and the output of the logarithm becomes the exponent. Well, 5 squared is just 25, and we get a pretty standard quadratic equation here. This is 3x squared minus 10x minus 25 equals 0. This happens to factor, but if you couldn't see how to factor it, or if it didn't factor, we would just use the quadratic formula. This is 3x plus 5, x minus 5. And so we get two solutions, x equals negative 5/3, or x equals 5. But notice that negative 5/3 isn't an allowable input to the first expression. You can't plug it into the second one either. Negative 5/3 isn't actually a solution. X equals 5 is okay. In fact, we'll check it all the way through. Log base 5 of 5 would be 1. In the second expression, 3 times 5 is 15. 15 minus 10 is 5. That's also log base 5 of 5. That's also 1. And at this point in your mathematical career, you probably know that 1 plus 1 equals 2, so this really is a solution. Let's do another one like that. See if you can do the first step. Log base 4 of x plus 7 plus log base 4 of x minus 5 equals 3. See if you can consolidate those logarithms on the left side. To consolidate those logarithms, you would multiply the inputs. So this is log base 4 of x plus 7 times x minus 5. And I would use the FOIL process to multiply that out. That's going to give us x squared plus 2x minus 35. And now we rewrite this in exponential form. See if you can rewrite this in exponential form. The input goes by itself on one side. The base of the logarithm is the base of the exponential expression. The output of the logarithm is the exponent. 4 cubed is 64. Again, this is quadratic, so you probably want 0 on one side. This is x squared plus 2x minus 99. This factors to x plus 11, x minus 9. And so we get two proposed solutions, x equals negative 11 or x equals 9. Negative 11 is not an allowable input to either expression. 9 is okay. We get log base 4 of 16, that's 2, plus log base 4 of 4, that's 1. 2 plus 1 is 3. What if the logarithms are on opposite sides? In our examples, all the logarithms were on one side and there was just a number on the other side. But what if you've got a logarithm on each side, like this example? Well, we'll just use a standard math strategy. This isn't specific to these problems, but just in general. Anytime you're doing a problem that looks different than something you've done before, see if you can make it look like something you've done before, and then just do what you've done before. This example says the common log of x plus 4 equals 1 minus the common log of 3 minus x. Well, we haven't seen anything like this before, but if we were to move the log of 3 minus x to the left side and rewrite that as the sum of these two logarithms, well, now we have done problems like this before. We know that we can multiply these inputs. So this is the common log of x plus 4 times 3 minus x. Multiplying that out, we get the common log of the negation of x squared minus x plus 12. Rewriting this in exponential form, we get the negation of x squared minus x plus 12 equals 10 to the first, because the base of the common logarithm is 10. 10 to the first is just 10. I would subtract 10 from both sides to get negative x squared minus x plus 2 equals 0. And then I'm personally more comfortable with a positive leading coefficient, so I would divide every term by negative 1. Gives me x squared plus x minus 2 equals 0. This factors to x plus 2, x minus 1. And so we get two proposed solutions, x equals negative 2 or x equals 1. Before you assume that negative 2 doesn't work, let's plug it in. On the left side we get negative 2 plus 4. That's 2. That's an allowable input. And on the right side we get 3 minus negative 2. That's 5. That's also an allowable input. Negative 2 works. Before you assume that 1 doesn't work, let's check it as well. 1 plus 4 is 5. 3 minus 1 is 2. Both of these are solutions. It's not always the case that if you get a proposed solution which is negative, it doesn't work. It's not that x can't be negative, it's the input to the logarithm that can't be negative. Negative 2 makes both of these inputs positive, so we're fine there. It's also not always the case that one of the two solutions has to be extraneous. Here, both of these work. You got to check. You can't make any assumptions like that. Here's another example with logarithms on both sides. Log base 3 of x plus 2 equals 4 plus log base 3 of x minus 1. When we have logarithms on both sides, it's a good idea to get everything to the same side. Now this is a little bit different because we have to subtract this logarithm to move it. So we get log base 3 of x plus 2 minus log base 3 of x minus 1 equals 4. We still want to consolidate on the left side so that we can rewrite this in exponential form, but now we divide the inputs. Rewriting this in exponential form, we get x plus 2 over x minus 1 equals 3 to the fourth. 3 to the fourth is 81, so that's x plus 2 over x minus 1 equals 81. Take this over here. Multiplying both sides by x minus 1, we cancel the denominators on the left side, leaving us with x plus 2. On the right side, we get 81x minus 81. And now we solve for x. I would subtract x from both sides and add 81 to both sides. So we get 83 equals 80x. Dividing both sides by 80, we get x equals 83 over 80. Is that an allowable input? Over here, 83 over 80 plus 2 is definitely going to be positive. When you add two positive numbers, you get a positive result. Over here, 83 over 80 is just barely bigger than 1. So when you subtract 1, you do get a positive result, and this just sneaks in. It's just big enough to be an allowable input. Let's try another one like that. See if you can do the first couple of steps to this example. The natural log of x equals 2 plus the natural log of x minus 5. First thing you want to do is get all of the logarithms to the same side. We're going to subtract the natural log of x minus 5. On the left side, that gives us the natural log of x minus the natural log of x minus 5, and on the right side we have 2. Now we consolidate and get the natural log of x over x minus 5 equals 2. And now we're ready to write this in exponential form. You just have to remember that the base of the natural log is the number e. So we get x over x minus 5 equals e squared. Now I know this looks funny, but don't do anything different than what we did last time. You're going to multiply both sides by the denominator, which is x minus 5. On the left side, the x minus 5's cancel, and we just get x. On the right side, remember that e squared is just a number, and so you can distribute it to both terms. This is e squared x minus 5e squared. I want to get all of the x's to the same side, so I would subtract e squared x from both sides. Let's take this over here. And we get x minus e squared x equals negative 5e squared. At first glance, it looks like we might be stuck, but remember, we can just factor out an x. So we get 1 minus e squared times x equals negative 5e squared. And now we divide both sides by 1 minus e squared. We get x equals negative 5e squared over 1 minus e squared. It might look a little nicer if we multiply every term by negative 1. 5e squared over e squared minus 1. Now 5e squared over e squared minus 1 is definitely a positive number, so we're okay on the left side. But it's not immediately clear if we can plug this into the right side, like is this bigger than 5? Well, if you use a little bit of number sense, you can tell that this is bigger than 5, because e squared divided by e squared minus 1 is going to be bigger than 1, and then we're multiplying it by 5. But that's kind of tricky to see. When you're not sure, just use your calculator to get a decimal approximation. We want to know if 5e squared divided by the quantity e squared minus 1. Make sure you put that in parentheses. Minus 5 is positive or not. And it is. That is an allowable input to this expression, so this really is a solution. X equals 5e squared over e squared minus 1 is the answer. Let's do one more like that. Natural log of 2x minus 1 equals 1 plus the natural log of 3x plus 1. I want you to try to do this one all the way through. Consolidate the logarithms, rewrite it in exponential form, get the proposed solution, and then check to see if it's an allowable input. Let's see. We're going to subtract the natural log of 3x plus 1 from both sides. The idea behind this is that this gets all of the logarithms on the same side so that we can consolidate. We're subtracting here, so to consolidate we divide the inputs. Now we rewrite this in exponential form. The input is equal to the base, which is e, raised to the first power. Well, e to the first power is just e. Now we multiply both sides by the denominator, 3x plus 1. On the left side, the 3x plus 1's cancel, and we get 2x minus 1. On the right side, we distribute the e, and we get 3ex plus e. Make sure you distribute that e to both terms. We want all of the x's on one side, and we want everything without an x on the other side. So I'm going to subtract 3ex from both sides. That'll move all of the x's to the left side. And because I've committed all of the variable terms to the left side, I want to move the constant to the other side. We get 2x minus 3ex equals e plus 1. We can factor an x out of this. This is 2 minus 3e times x equals e plus 1. Dividing both sides by 2 minus 3e, we get x equals e plus 1 over 2 minus 3e. That's our proposed solution. Is that an allowable input? Well, we'll run to the calculator and approximate it, but again, if we use a little bit of our number sense, we can see that this number is actually going to be negative. E is around 2.7, so the numerator is around 3.7, and in the denominator we have 2 minus 3 times 2.7. That's going to be a negative denominator. The numerator is positive, the denominator is negative, so this quotient is negative. And when we plug that negative number into the left side, 2 times the negative number would be negative, minus 1 will still be negative. So this actually isn't going to be a solution, and this equation has no solution. Which I know is a little bit annoying to do all of that work just to find out that the equation doesn't have any solutions, but sometimes that happens. Some equations don't have solutions. If I went through that check a little bit fast, another way that we could do this is to approximate this with the calculator. Parentheses in the numerator, e plus 1, close the parentheses, divided by parentheses in the denominator, 2 minus 3e. Notice that because I'm not raising e to a power, I'm using the obelisk key instead of the natural log key. So that number's around negative 0.6. I want to know if this is an allowable input to the left side, so I need to take 2 times that number minus 1. I suppose there's nothing wrong with using a decimal approximation here, but we saw in a previous example that sometimes it's pretty close to whether or not you can plug that number in. So the safe play is to try to use this exact value. And the way that I'm going to do that is I'm going to tell the calculator to use my previous answer. I want to plug this into the expression 2x minus 1 to see if it's an allowable input. So 2 times the previous answer. To get the previous answer, you push second and the negation key. And that says use the output of my last line as this value. Subtract 1 from that. That's definitely negative. That is not an allowable input to the left side, so we have no solutions. You've got to check for those domain restrictions because logarithms only allow positive inputs. So we ran through a pretty good selection of equations that can be solved using our new properties. You saw we also had to call back on some old ideas as well, like the fact that logarithms are one-to-one, or our translator to go from logarithmic form to exponential form. Those are still involved too, but now we're also using our new properties. Make sure you try some examples on your own. Find examples of every type. So examples where every term is a logarithm, examples where all of the logarithms are on one side and there's a constant term on the other side, and then examples like our last couple where there are logarithms on each side as well as a non-logarithmic term. If you have any questions for me about the examples here or any examples you're trying on your own, be sure to reach out to me. You can find me in an office hour or you can send me an email.